Welcome to Unit 8 of our course, where we'll discuss network security in the context of IPOP. So, to overview the security mechanisms that are available, they're basically security mechanisms implemented in the overlay itself, supporting point-to-point and end-to-end security that's implemented within the IPOP code base with primitives that follow public key infrastructure techniques. So, private public keys and certificates. There's also mechanisms external to IPOP that can be tunneled through the overlay, IPsec being a key mechanism for network security here. IPsec can be tunneled transparently over IPOP because it is layered on top of IP itself. And that's good because it allows us to reuse existing kernel software implementations and tools that manage IPsec. So within the overlay, the IPOP software uses a PKI-based public infrastructure security framework, and there are two ways PKI techniques can be applied in the overlay. One is point-to-point for each overlay edge, and the other is at the IP layer, end-to-end authentication and encryption of IP messages. So point-to-point security is useful in a case where you would like to ensure that nodes that join the overlay have been vetted or signed by a certificate authority. So the model that is used here is that there is one certificate authority that signs for an overlay. So let's say you would like a private P2P overlay for your virtual networks. There's a certificate authority that signs node certificates for each node that joins the network. And in this example, we have, let's say, node number 5. It's only able to create edges to nodes 4, 6, and 1 if it produces a valid certificate that is signed by the certificate authority trusted by N4, N6, and N1. Once it does that, it joins the network, and all the communication between these nodes is secured by cryptographic techniques. Now this is a point-to-point mechanism, so the keys are shared. There's a session key, encryption, decryption key for the edge between 1 and 5, and messages are decrypted and encrypted again every time they go through a hop in the overlay. End-to-end security is a technique that is applies at the IP layer in the case of IPOP, and here we also continue with the model of a certificate that is signed by a certificate authority for each node, but here we look at the end-to-end path between two nodes that are communicating over IP. So let's say N1 sends an IP packet to N7, that's going to be encapsulated and encrypted with a key that's shared between 1 and 7, and it's not going to be decrypted and encrypted again by the intermediate nodes. One question that arises is, given that you have support for security, how do you configure nodes in a way that is seamless and facilitates the deployment of these VPNs? And as part of the IPOP infrastructure, or a complement to the IPOP infrastructure, is this system called GroupVPN, which enables users to manage VPN membership. And the key approach here is that we build upon the namespace abstraction that we saw earlier, which separates IP address spaces. And for the configuration of the endpoints with VPN security credentials, we use a web-based front end to automate the process of signing certificates for the end users. So you have a decentralized routing fabric, but you have a centralized management of users and certificates through this web-based interface. And that's useful when you have, again, a single trusted authority that signs for, allows nodes to join a particular VPN on top of IPOP. So users can go through this website, configure a new VPN group, configure its namespace and its address allocation, And the group owner also uses the website to ask users to join the overlay and to allow or deny users into the overlay. So this is motivated by a model of simple management of collaborative environments by users through a web-based user interface, and hiding from the users the complexity associated with PKI management. So generating certificates, signing certificates, etc. So how it works is you have, through the web server, a user, which is the equivalent now of a certificate authority. Alice, in this example, creates a new group VPN. Users request to join this Alice group VPN, and Alice will have to authorize them in order for them to become members of this group. Once they are members of this group, they are able to download from the website the configuration for their VPN endpoints. And at that point, they can deploy nodes on the virtual network, and these nodes will be able to communicate with end-to-end encryption and privacy and authentication. So this is what the user interface looks like. Here's a snapshot showing here in this highlighted box a number of user-created groups. Any user can create their own VPN on top of a public P2P overlay. And once inside a group, when a group is created, the owner of the group decides on its namespace and on the IP address space, the configuration of the IP address space for that virtual network. And the management of the group can allow or deny users to join the VPN. And these are users of the website, and once they are allowed to join the VPN, they're able to download the VPN configuration for their endpoints. Another mechanism that was mentioned earlier is layering IPsec over IPOP. And the mechanism here is used for end-to-end IP layer security, not for point-to-point security. But the benefit of having IP over P2P in IPOP is that IP packets can be tunneled, and IPsec layering on IP is supported without any modifications. Now, the main challenge with IPsec is, again, configuration of the endpoints with security credentials. So tools built for IPsec have been tailored for typical VPN setups, which are mostly static, configured once between a small number of networks and not reconfigured dynamically, whereas IPOP virtual networks are quite elastic. Nodes can join and leave dynamically over the lifetime of the VPN. So the general approach here is, again, to use a public key infrastructure with a certificate authority that signs certificates for the endpoints. And this leverages the fact that IPsec already supports this model. And it's possible to embed the namespace of an IPOP virtual network on the certificate that's signed for IPsec, or also embed virtual IP addresses so that they are checked as identities when nodes try to connect to each other over IP. So in this model, again, Alice here generates and signs host certificates. Let's say that there's a user that's deploying a virtual private network across multiple instances, or a middleware that deploys virtual private network nodes across multiple clouds on behalf of a user. So this trusted entity generates and signs host certificates, the X509 standard, binding the namespace of the IPOP VPN as part of the signed certificate. And nodes are deployed with these node certificates on the overlay. For example, these certificates can be transferred to virtual machines when they are instantiated at the time of contextualization, at the time that the virtual machine is configured for the first time. From the perspective of applications, again, they see IP. They do not have to worry about the configuration of security. So if an application sends a message, let's say N1 sends a message to N7, this is encapsulated in IPsec, so the payload is encrypted if you select to use encryption in IPsec, and then the IPsec message is encapsulated into IPOP and sent over the overlay. And that is, again, decrypted and decapsulated at the other endpoint, N7, when it's received. One of the benefits of having separate virtual address spaces and the ability to have isolated networks with isolated network masks is it facilitates significantly the configuration of security. So you don't have to worry about configuring policies for each possible IP pair of nodes that join the network. Rather, let's say if you define a virtual network address space of this type, a private network address space with a 16-bit network mask, the only configuration you need to set up for IPsec would look like this. You can set up configuration for an entire net mask that forces any traffic within this network address space to go out using IPsec, and here using transport mode of IPsec with security encryption and encapsulation, as well as any packet that comes into the network has to be authenticated and decrypted using IPsec. So with 2 lines of configuration, you're able to secure a virtual private network that may have up to 2 to the 16 nodes connected to it. So that concludes the discussion on security, and the next unit we're going to begin looking at applications of IPOP.